Welcome everyone. So yeah, I know it's early. It was very early for me on a Sunday morning. So I hope you've got coffee. I'm looking forward to caffeinating and a comfy chair. The image that's presented here is our virtual coffee shop that features in Autopilot simulations. And we call one of the simulations we have is called Mars, funnily enough, which stands for Massively Awesome Reality Simulator, I think is the backronym that we came up with for that. So I'd like to thank Parallel Domain and CVPR and the other sponsors for hosting the workshop and inviting me to share a collection of practical learnings that I've made training ML computer vision models using simulated data. So just to talk a little bit about about what I'll spend the time on today. We know deep learning success requires three high quality ingredients: the algorithms, compute, and data. So the simulation training team at Autopilot focuses on combining object interactions, graphical assets, rendering in a runtime environment with the goal of providing data sets with a high level of quality relating to image output and ground truth labels. So I'd like to cover tips and tricks across these three categories in the order that they kind of occur in the wild. So we're going to talk about how to choose a project to train synthetic data, and then generating that data, and then how you use that to produce better models through training and analysis. So before we really get into the specifics, I wanted to introduce or give an overview of the synthetic data pipeline at Autopilot. So the sim training team is really well supported by the specialized content artists and core engineers that we have inside the team, but as well, we've got infrastructure, data analysts, and ML engineers themselves. And we combine all these in a collaborative effort to operate quickly and at scale. But we need to cover all the disciplines independently within our team to be responsive. So our data pipeline consists of the following components from left to right. The first advantage is that the Tesla fleet is huge. We're almost 2 million vehicles on the road, collecting telemetry from everywhere. So for example, the image on the left is an overlay of the San Francisco downtown area with all of the training examples organized into tiles. So we take that kind of rich data and extract kinematics, camera image, and other real-time data values and process them with offline models. So the kind of, auto label for foundational models that produce different specialized data from lane graph, ground truth, mesh data, 3D occupancy, and other signals. So we take these annotations and combine them with other offline data sources, things like OpenStreetMap, GIS data, and we feed that into a procedural mesh pipeline, which is created in Houdini. So that was the subject of last year's AI Day presentation, if you're able to catch that. And that produces the driving environment. And then finally, we render the environments in a variety of different image producers, depending on the application. So we do use Unreal, both the legacy renderer and also the Lumen. And then we have our own ray tracing, real-time ray tracing renderer as well. And so we mix and match those image producers depending on the data set projects that we have going. And what's interesting here is there's a feedback loop here back to the start of the pipeline. So once we produce these simulated driving environments, we can then overlap them with the real driving data that we're getting. So the context of this presentation includes training perceptual models with different modes and different output spaces. However, the data that drives all of the training is sourced from the same pipeline. So I want to talk a little bit about choosing synthetic data projects. So, you know, the seasoned AI and ML researchers and engineers among you all, and at Tesla, always prefer the full strength real world data sets over synthetic. And for that, there is no fault. Autopilot has a huge advantage of sourcing full self-driving data from the fleet and generating high quality ground truth using really large models that benefit from the offline compute and also the extended temporal computes that you gain advantage of when training offline. And we want to ensure that our systems are super safe. And this means using synthetic data sets in a complementary fashion, especially when training models from scratch. If a data set content is not hard to source, hard to label, or otherwise obtainable from the real world, then it may be suboptimal to compete with the real world. So the guidelines presented here on this slide speak to using the superpowers of synthetic data. We can use our simulator to permute these hard to find examples that are too dangerous to source in the real world. So in the top right is an example of a very effective synthetic data set where we took high quality 3D scans of car wrecks and then permuted those into really difficult lighting environments, high speed at highway. So the image space examples there are from our simulator, and you can see how difficult it would be to spot an unlit wreck at a highway, and I definitely wouldn't want to be in charge of collecting that data, especially at over 70 miles an hour. So that's a great example of where we use the superpowers of synthetic data to capture a realistic situation that's a bit dangerous to collect. Conversely, there's also situations that are pretty unlikely to happen. So maybe in Canada, you might get a bear running on the road in this bottom animated example. But there's a whole lot of like crazy situations that we can glue together with the simulator here and extract kinematics and object positions, velocities, trajectory, ground truth, that kind of thing. So once we've picked a data set that is suitable for a synthetic data project, we need to generate data using the simulator. So one of the core issues with producing a huge quantity of training data is quality. How can you ensure that every clip, that every training example that is produced with a simulator is valid? So one approach is to build dataset features iteratively, ensuring valid features at every step and pruning out aberration wherever it's observed. So a key piece to doing this is the ability to produce the generation of every training example in the dataset. So the context here is on the top right, you can see a random generation for the interiors of garages that we use to train an occupancy network on indoor scenes. So it's great when everything works, but there's always going to be outliers in a random generation. What happens when we generate a closet with an open door that happens to collide with a piece of geometry of a vehicle that's in the garage? So one way to combat this, if we sort of take a look at the Python pseudocode presented on the left, let's say your configuration has a method to add a random feature to the training data. And usually training data sets are comprised of a lot of aggregate steps with random generation throughout them. So before you start throwing the random generation around and calling numpy.random methods throughout the generator, it's really important to set the seed up and encode it into all the simulation run identifiers. Then you can start building configuration that works. You start with 100% human verification in small batches of like 10 or 100 examples. And then when you move to generating this data at scale, no matter where you observe the dataset examples, if it's on CI or on a training cluster or even on a local machine, you can take that run identifier, it's like that's highlighted in purple here, and then run that back through the generation pipeline and fix any problems and stamp out any aberrant training examples. It's also very handy to encode this small string, and you can pass it around and share a huge amount of data very quickly. So perception models are extremely specialized, and the data sets should be as well. We find it's of very little utility to produce a huge amount of nominal training data. And so this is true for autonomous driving, which requires high detail spot coverage of a variety of problem cases for specialized perception tasks. This is particularly true sort of when you consider the powers of synthetic data. We want to complement the real world data that we can get from the fleet. So it's great to aim for maximum diversity, as we were covering sort of in the generation slide, but it can really hurt quality. So we need to think about the model that's being trained and what features it encodes. And we'll touch on this later. There are dimensions that should attract variation and verification when you generate, and this should be reflected in quantitative diversity metrics, and that should change with every data set. So there's another contrived Python code example here, where we've defined a function that returns some data that defines simple uniqueness constraints over the simulation generation here for just map and lane. So we can see we're just returning a tuple that defines a unique map and lane. But what's important about this function is that it should be overridden for every perception task and potentially every data set. So what this does then is when the configuration is utilized, you can report quickly how the generation performed. There's, of course, like a lot more advanced diversity analysis that you can do, k-means clustering algorithms, that kind of thing, and that's the subject of a different talk. But what I'd like to focus on is the kind of important everyday reminders in the diversity that the network that you're training cares about. And so then when you interact with your data set on a command line, you can, it's cute to print out a little smiley face there, depending on how the data set was generated. And that helps keep it front of mind for anyone working with the synthetic data set. So there's some more examples of like tooling like this that we've created to check specific data set diversity for specialized networks. So on the image at the bottom right, that's a case where we care about the lane and intersection connectivity of the network. So we've got a complicated intersection there showing what turns are capable. And so that's used as a thumbnail when scrolling through a huge data set, so we can see really visually what's going on. On the top right, similarly, it's a different network where we want to identify the traffic distribution across highway lane network by clustering the colors. So it's very easy to quickly see how the random generation is spatially affecting the data set. So another topic to talk about during generation is having the predictions in the loop with generation. So the chances are when you generate a synthetic data set, you're generating on hardware that has ample CPU and GPU resources to run similar models to the ones that you're trying to train. And it's really beneficial to check the performance of the current model that you're trying to train against the new data set that you're creating in some arbitrary but relevant metric. It doesn't have to be the full weight model. So the idea is to create like a collective heuristic that follows both your intuition about the data set that's being created using the context and from how you've chosen to create the data set project. And then also the evaluation metric is super important. And that's the metric that you'd use during training. If you have the luxury of overage, like creating more data than you need, then this model prediction score can be used to sieve the final data set and separate the good examples from the less useful. So here's an example in practice. So the top two images are a simulation of the fisheye and narrow camera on a Tesla with a random moving object that's been generated in front of in the drivable space. So it's a small child's rolling toy. And it's crossing the drivable space from right to left. And then in the bottom left, these are the predictions. It's an aggregate 3D prediction. So we're looking back from the object towards the vehicle. And so the overlay, it's showing the predictions of two separate networks against the ground truth, the synthetic ground truth in red. So the ground truth's in red. We've got in the background, there's a orange blob, which represents the occupancy prediction. So the in 3D space, or the occupancy of voxels for the object. And then as well, there's also overlaid in purple an object detection network predictions. So when we generate this data set, the same time we're rendering frames, we can also run these models in the loop and predict a score and produce a heuristic here. And the heuristic's really simple, doesn't slow down the generation of the data set. It's simply just distance of the core voxel prediction to the transform of the synthetic object, that kind of thing. And what that enables you to do is you produce this score. It's a discrete metric, and it allows you to order every training example in the data set to maximize the value. So in combination with other analytical tools like high loss, the impact of each data set can be optimized, and we can only train on the most valuable examples. So the final objective of all this effort is to deliver data sets that are included in production model weights that deliver improved in-car performance. And full self-driving is a compound task that's full of lots of different meta tasks. And this means metrics drive everything. There's no point starting a new data generation project without first identifying what perception metric we wish to improve. And what the exact effect of the synthetic data that we create has on the neural network training. So this is intrinsically linked with the diversity metrics that we talked about. So the example here, the training data we produced was for vulnerable road users, so people on rideable scooters and bikes, that kind of thing, with trajectories that are dangerously close to a Tesla. So once again, pretty perilous to collect from the real world. So we did a series of fine-tune experiments, and we undertook, various oversampling rates and different hyperparameters to achieve a small but marked improvement in the velocity prediction for this safety critical case. And what's important here is like to adjust expectations. If we can if we can calculate the value of the training examples that we're presenting to the neural network, and we can achieve these repeated and regular improvements in metrics, then it's all about taking the win. And we work in really close collaboration with the ML research teams at Tesla, and we focus on these use cases that produce real world safety impact. So the example here is that we can use synthetic data to improve something like the trajectory prediction for close by objects and solve real world safety cases. So what we do with synthetic data at Tesla is necessarily empirical. It means the intuition is gained through experimentation. So If you're not able to iterate and experiment quickly, then the job is infinitely more difficult. So it's about running ablations, trying new ideas, improving throughput. So we basically take the attitude that you can't fail as long as you consistently measure data set diversity, check the ground truth fidelity, and that's just like a huge one. Couldn't stress this enough. I almost wanted to every slide, put a check the GT little box on there, because even when you're so sure that everything's perfect, there's always more you can do. Checking the content quality and concentrating on the effectiveness with the metric. The rest comes down to hyperparameters and the expectation to move the needle. So what we were talking about previously, like if you can take a 3 to 4% improvement in a important critical metric, then that's great. So this example shows how this iterative approach I've been presenting can be when the foundations are solid. So we're fully bootstrapped to drive model improvements with synthetic data, and it's a kind of a data-driven approach at huge scale. So this is an example here where we're using fine-grained metrics evaluated at training checkpoints to ensure the safety of our systems. So we also pay really close attention to things like the alignment and accuracy of our virtual cameras, matching the variability of the intrinsics and extrinsics of the cameras, and we match that with what we measure at the factory. And we also fully simulate all of the systems of our vehicles in FMUs to ensure the accuracy of our simulation. So this example, we produced 13,000 clips of just the backup camera from a Tesla with all kinds of objects, VRUs in various positions, lighting conditions and weather. And we're able to, take that small improvement in a critical metric and do that repeatedly for every successive model generation. So I'd like to tell you a little bit more about some of the ways we've used this method. I've got kind of 3 case studies here that cover different types of neural networks. So this first one is about the lane graph topology detection. So we wanted to train and improve the prediction of lane graph connectivity for turning lanes. And so to do this, we produced a kind of continuously variable lane graph paint material and shader. And then we went to our fleet data and sourced intersections that had a high frequency of intervention from full self-driving that was cross-referenced with turning maneuvers. And then by reproducing the driving environment with variables with diversity added for this lane paint and the vehicles that obscure the lane paint, we're able to markedly improve the predictions in lane graph topology. Moving on to an object detection example. The detection of fast-moving animal VRUs, vulnerable road users at night, was improved, generating a wide variety of different animals crossing the road, crossing drivable space in all kinds of lighting conditions. You can see how difficult it is to see some of these examples in, say, like a fully distorted fisheye camera. And yeah, it's interesting to see there's more collusion between the object detection network and our BEV style occupancy network. And if you're interested in that kind of shared architecture for vector space features between networks that have 2 different output spaces, there's another talk by my colleague Phil Dewan today that I'd recommend checking out. And the last case is kind of a pure object detection example where we're able to improve the detection of small small VRUs, small humanoid VRUs, by randomizing skeleton mesh poses. So some overlap with the last talk, Junha's talk. We use an approach where we perturb the constrained skeleton mesh positions of our actors, and we have a library of over, I think it's about 200 different meshes that all have a shared skeleton. So we produce a random poses by perturbing the physics skeleton mesh, and then retargeting that to a huge different a library of humanoid meshes there to produce this data set. And then we combine that with the rideable scooter, bicycle, and other assets to produce quite a over a 12% prediction accuracy and recall boost to that stationary approach to one of these vulnerable road user cases. So once again, thank you to the hosts and Parallel Domain for hosting. It's my first CVPR, and I'm having a great time so far. We're hiring, and we're really building up a huge collaborative team. So if you know of anyone, or if you're yourself interested in joining this effort of training large ML systems with both real and synthetic data, then please visit the Tesla booth in the expo and join us for happy hour on Wednesday night. Thanks so much.